Hi, this is another quick exercise on Euler's method. Euler's method is pretty useful to approximate how a solution of a nonlinear differential equation, or even linear, but in nonlinear cases, that's where it's useful. How that looks. So what is Euler's method? Euler's method. It's a recursive definition that basically does the following. So say I have a curve like this, and I don't really have a way to find this curve explicitly. So what I can do is I can say, well, I have a value for the slope of the curve at any point. Like I have an expression for the slope of the curve at any point. That's what it means to have a first order differential equation here. That's the slope of y. And we can say that this is y. Well, and to be even more precise, we'll say that this is x. So when I have this, how do I get this slope at this point? Well, it happens at the point x naught. So really, well, I'm going to call it x naught. So really, you just want to take this and evaluate it at x naught, right? Because that is the expression for the slope. So you're just going to do f. It's not going to be f of x. It's going to be some other function, g of x, evaluated at x naught. Or in other words, you can say that that is the derivative of the function f of x at x naught. That gives you the slope. Well, now, how do I specify, though, that I want to start from here and then approximate some values that are close to this function by going up on this line or down on this line? Well, I need to specify in some sort of way that I am starting from an amount up and an amount to the right. So I'm shifted to the right by an amount x naught, and I am shifted up by an amount equal to f of x naught. However, we do not have f of x naught. So what we get really is that if I want to find a value for f of x, what I can do is I can do this, shift it by that amount x naught, and then add f of x naught. So we don't have a value, we don't have an expression where we can put whatever x naught we want, but we do have some initial condition. This is the equivalent of f of x naught, where my x naught is 1 and my y corresponding to that x naught is 5. And this would be my y corresponding to that. This would be my y. So now I can substitute the values in. But we need to realize another thing. This is telling us the x that we want to end up at. So we're then going to have an h amount, and we're going to end up at x1, which is going to be some other value right here. And we need to realize that there is an error here. And the farther you go, could have a larger error. So what do we do once we get to x1? Well, once we get to x1, we say, okay, well, what is the slope at this point? Well, the slope at that point is going to be, so let me rename this as y1. Well, the slope at that point is going to be what? It's going to be f of prime of x sub 1, and it's going to be shifted by x sub 1, and it's going to be evaluated at x sub 1. And what is that going to be? Well, that's going to be our y sub 2, right? Now, we can rewrite this as y sub 2 is equal to f prime of x sub 1 times x, which is going to be x1 plus h minus x1, right? Because this is equal to x naught plus h. And so we can do the same later. And this part right here is just going to be f of x1. So these two cancel out, and what we're left is y2 equals to h times f prime of x sub 1 plus f of x sub 1. Where f of x sub 1, we said it's y1. So we get h times f prime of x sub 1 plus y1. And so, as you see, every time we have a recursive definition. So now that we did this exploration, let's try to write a formula for y sub n is going to be equal to the y that came before, so y sub n minus 1, which was the shift, this one right here, plus we're going to add the slope at y sub n, right? H is going to come from this, and then we have the slope at x sub n minus 1 right here, and that is it. We can have a table here. Let me make a little bit of a table. We can have a table with values down here, and we can say that this is my x, that this is my y, and this is my dx dy. So, where are we starting here? We're starting at 1. So if we start at 1, we know that our y is 5, and our slope is going to be equal to putting x and y into this. So 2 times 1 is 2, minus 3 times 5 is negative 15. So 2 minus negative 15 is negative 13, plus 1 is negative 12. So our slope is negative 12. Then what we want to do is we want to add 0.1, because they're telling us to do it in 0.1 increments. So this is going to be 1.1. What is y going to be? Well, negative 12 is the slope if you go, and I don't know why I wrote dx dy, I meant to write dy dx. Negative 12 is the step, the change in the y if you go by a step of 1. Well, what if you go by a step of 0.1? Well, then that's going to be 1.2 negative. So we're going to subtract 1.2 to this, which is going to be 3.8. And then we're going to calculate, we're going to put these into the slope equation. So if we put those into the slope equation,